Ever wondered about the world of heterocyclic chemistry and its impact on pharmaceuticals? Well, prepare to be intrigued. Heterocyclic chemistry, a vast and complex domain, forms the backbone of many life-saving drugs and medicines. It's like the invisible hand that guides the world of pharmaceuticals. Imagine a universe where atoms are stars and molecules are galaxies. Now envision a cluster of these galaxies, each one unique, and each one formed by a different combination of atoms. That's heterocyclic chemistry for you. These compounds, known as heterocyclic compounds, are composed of atoms of at least two different elements, forming a ring structure. From the coffee you drink in the morning, which contains the heterocyclic compound furan, to the life-saving drugs that treat a myriad of diseases, these compounds are omnipresent, silently shaping our daily lives and well-being. So buckle up as we take this fascinating journey into the world of heterocyclic compounds. Each compound in heterocyclic chemistry plays a unique role, much like characters in a play. Let's meet some of these characters, starting with furan, a five-membered ring with oxygen as a heteroatom. Thiophene, on the other hand, swaps that oxygen with sulfur. Pyrrole, a nitrogen-containing five-membered ring, is another key player. Introducing pyrazole and thiazole, compounds with nitrogen and either nitrogen or sulfur respectively in their five-membered ring structures. Imidazole, oxazole, and isoxazole are similar, but they spice things up with a second heteroatom in the ring. Hydantoin, however, takes a different approach, with a six-membered ring featuring two nitrogens and one oxygen. Moving on to six-membered rings, we have pyridine, a simple structure with one nitrogen. Pyridazine, pyrimidine, and pyridine follow suit but vary the positions of their two nitrogen atoms. Indole, a fusion of a benzene and a pyrrole ring, adds a new twist to the story. Benzfuran, benzthiazole, benzimidazole, and benzoxazole are intriguing compounds where a benzene ring is fused with furan, thiophene, imidazole, and oxazole respectively. Quinoline and isoquinoline take a similar approach but with a benzene and a pyridine ring. Quinazoline and cinnoline, with their fused six-membered rings, each containing two nitrogens at different positions, are yet another fascinating set. Purine, a fusion of pyrimidine and imidazole rings, is a compound that truly stands out. Xanthine and pteridine, derivatives of purine, are also worth mentioning. Last but not least, we have coumarin, an oxygen-containing compound with a fusion of a benzene and a pyrrole ring. Aromatically delightful, it's often found in fragrances and certain foods. Each of these structures is numbered in a specific way, starting from the heteroatom and moving around the ring. This numbering is crucial for identifying the position of substituents, which can significantly alter a compound's properties. Isn't it incredible how each of these compounds has its unique structure and numbering? Now, you might be wondering, how do these compounds affect pharmaceuticals? Well, let's dive right into that, shall we? The world of medicine is incredibly indebted to heterocyclic compounds. Each compound we've discussed so far plays a unique role in the development of different drugs, acting as the backbone of many pharmaceuticals. Take, for instance, furan. This oxygen-containing ring structure lends its stability to certain antifungal and antiviral drugs. Then there's thiophene, a sulfur-containing ring, which is found in drugs used to treat conditions like schizophrenia and depression. Pyrrole, a nitrogen-containing ring, is found in drugs like tolmidine, used for its anti-inflammatory properties. Pyrazole and thiazole, two more nitrogen-based rings, are found in a range of drugs from anti-inflammatories to antibiotics. Imidazole, another nitrogen-based ring, plays a crucial role in antifungal drugs. Oxazole and isoxazole, both oxygen and nitrogen-containing rings, are found in antibacterial and antifungal drugs. Hydantoin, an interesting compound with both oxygen and nitrogen in its ring, is used in anticonvulsant drugs. Pyridine, a six-membered ring with one nitrogen atom, is found in drugs like bedaquiline, used to treat tuberculosis. And there are even more complex structures. Benzimidazole, for instance, is utilized in antiparasitic drugs, while quinoline and isoquinoline are used in anti-malarial drugs. Purine, a two-ring structure, is a key component of many drugs, including those used to treat gout and leukemia. And lastly, coumarin, a compound with a pleasant odor, is used in drugs that thin the blood. Each of these compounds, in their own way, contributes to the wide array of drugs that help us combat diseases and maintain our health. They may be small in size, but the impact they have is nothing short of colossal. It's astounding how these tiny molecules can have such a huge impact on our health, isn't it? So, what makes heterocyclic chemistry so special? Let's delve right in. Heterocyclic compounds are like the chameleons of the chemistry world. They have this uncanny ability to change their properties and behavior based on their environment. This adaptability is a result of the unique structure of these compounds, which contain a ring of atoms, where at least one of those atoms is not carbon. This atom can be oxygen, nitrogen, sulfur, or any other element from the periodic table, which adds a layer of complexity and versatility to these compounds. Now, why is this important? Well, this flexibility allows heterocyclic compounds to perform a wide variety of functions. It's like having a Swiss Army knife in the world of chemistry. They can act as catalysts, accelerating chemical reactions, or as inhibitors, slowing them down. They can bind to other molecules, changing their properties or behavior, or even act as a scaffold, providing a structure for more complex molecules to build upon. But the real magic of heterocyclic chemistry lies in its impact on the pharmaceutical industry. Many of the drugs we use today, from antibiotics to anti-cancer agents, contain heterocyclic structures. Take, for instance, furan, a 5-membered ring with an oxygen atom. It's found in many antimicrobial and antifungal drugs. Or consider pyrimidine, a 6-membered ring with 2 nitrogen atoms, which is a key component of antiviral drugs. These compounds are not just important for their medicinal properties. They're also crucial in the development of dyes, pigments, and electronic materials. Even the colors we see in fireworks are a result of heterocyclic compounds, reacting and releasing energy in the form of light. So you see, the magic of heterocyclic chemistry is not just in its complex structures or its diverse properties. It's in the way it touches every aspect of our lives, from the medicines we take to the colors we see. It's fascinating to see how the world of chemistry can weave such magical stories, don't you think? Before we say goodbye, let's take a moment to reflect on what we've learned today. We've journeyed through the fascinating world of heterocyclic chemistry, exploring the structures, numbering, and corresponding drugs of compounds such as furan, thiophene, and pyrrole, among others. We've seen how these compounds, with their unique structures and properties, are not just abstract concepts in textbooks. They are integral parts of our everyday lives, playing pivotal roles in the pharmaceutical industry. From the painkiller pyridine to the antibiotic quinoline, these compounds are the unsung heroes in our fight against disease. We've also seen how heterocyclic chemistry is a field that continues to evolve and surprise us, with new compounds and applications being discovered all the time. As we've seen, it's a field that is as complex as it is captivating, a testament to the beauty and wonder of chemistry. Subscribe for more because you won't find me later. Remember, the magic of chemistry is all around us, waiting to be discovered. Until next time, keep exploring.